Welcome to PW. Please let me know by writing in the comment section, beta ji, whether audio and video everything is perfect or not. So, till yesterday we have completed K-map and gray code. So just let me know by writing in the comment section that all of you are ready now. All of you are ready now. Please let me know by writing in the comment section, beta ji, that audio and video is going okay. And all of you are ready for this session. Great. Allow me to check as well. So audio, video, everything is perfect. Audio, video, everything is perfect. Great. Now I can see the audio and video, everything is going perfect. Okay. So till now we have completed gray code and K-map, and also we have learned about the EPIs, essential prime implicant, concept of don't care, how to find the minimized expression, as well as one question I have given to you in the last lecture, where we have designed one vegetable, goat and dog based combinational circuit. Is it okay? So if you remember, I have followed a very small steps to design that desired combinational circuit. Okay. So in this class, I am going to discuss first thing, that is introduction to the combinational circuit and procedure to design combinational circuit. Later on we will move towards comparator, half adder, full adder, half subtractor, full subtractor, and in the last I will move towards the binary number system. It is not binary number, just a representation only. Okay, that is all you needed for the gate. Then ones and twos complement concept, and the later on your overflow concept. That is very important for before studying group adder. We must have to follow the overflow, concept of overflow. Okay, so all these topics I am going to discuss in today's class. So all of you have to sit with a full concentration. Is it okay? Yesterday you didn't give Telegram QR, sir. Beta, Telegram QR is already mentioned in the description of the video. If you go with the first lecture video in the same channel, if you find in the live sessions, there is the first lecture, and in the first lecture when you see in the more section of the video, you will get all the Telegram channel description along with the Telegram Varun sir PW. Okay, is it okay? Great. Now let's move towards combinational circuit. I have shared the PDF onto the Telegram as well. So all the classes PDFs are already available on the Telegram, as well as you can get on the free sessions of the PW courses in pw.live app. Okay. So great. Let's start. Okay. So please observe combinational circuit. There are two. The entire digital is defined in two different domains. One is called as a combinational, and another one is called as a sequential. The basic difference between the combinational and sequential is in a combinational circuit, output only depends upon the input applied. However, in a sequential circuit, output depends upon the input as well as the previous state. Is it okay? So the basic difference is, in combinational circuit, whatever output, it is based upon the input and combinations only. In sequential circuit, output depends upon the input as well as previous state. So there is no memory element required in combinational circuit. However, to store the previous state, we must need one memory element in the sequential circuit. So your entire digital electronics is divided into two parts. Okay, one is combinational and one is sequential. In sequential, memory elements are required. In combinational circuit, memory elements are not required. Output only depends upon the input combinations. Is it okay? Great. So please write down. Please write down, beta ji. It is the interconnection of logic gates. It is the interconnection of logic gates whose outputs are determined from the present combination of the inputs only. Whose outputs are determined from the present combination of the inputs only. Is it okay? Great. Now please observe. So we have maybe n number of inputs and maybe we have n number of outputs possible in the combinational circuit. Now the first question is how to design any desired combinational circuit. If you want to design any desired combinational circuit, you must have to go with the 4 steps only. What are the 4 steps? Now please observe and please mention in your notes as well. Please observe here, sir. The first step is to identify input outputs and their relationship. First step is to identify input outputs and their relationship. Is it okay? Second step is construct truth table. Whatever you have identified the input outputs and the relationship, based on that you have to construct truth table. Is it okay? And step number 3, from the truth table you need to write the logical expression of the output and minimize it. So step number 3 is write the logical expression and minimize it. Write the logical expression and minimize it. And step number 4, implement the logic circuit. So logically, if you think now, only 3 steps are required to design any desired combinational circuit. Any desired? Yes. What are the different combinational circuit? Adder, subtractor, multipliers, okay, parallel adders, group adders, serial adder, your BCD to 7 segment displays, okay, BCD to access code converters, multiplexers, demultiplexers, decoders, encoders, all these are the part of the combinational circuit. So means we can design anything, sir. Whatever you are saying, all those names can we design? Yes, you can design by just following these simple 4 steps. You need to identify the inputs and outputs, construct truth table, write logical expression and implement the logic circuit. That's all we have to do. Okay, sir. Let's understand with the help of one question. Okay. Have you remembered yesterday we have completed gray code. Yesterday we have completed gray code. What is special in the gray code? In gray code we have seen we can convert binary to gray code and gray code to binary code. And a gray code is a one unit distance code in which successive numbers will be differ by only 1 bit. Let's try to design a binary to gray code conversion circuit. It is a combinational circuit. Yes, sir. We are giving binary and we want gray code. So if we want to design a combinational circuit, binary to gray code converter circuit, can we design by using these 4 steps? Absolutely yes. Let's try to design. Okay. So these are the different types of combinational circuit that we have to study. Okay. Before moving towards gray code, I am just writing this. So comparator, adder, subtractor, multiplexer, demultiplexer, decoder and encoder. So basically these topics we have to study in the combinational circuit. Is it okay? Yes, sir. Now please observe here. Let's try to understand the design of any desired combinational circuit with the help of one question. So please write down. Design a 3-bit binary to gray code conversion circuit. Design a 3-bit binary to gray code conversion circuit. Design a 3-bit binary to gray code conversion circuit. So first of all, we need to understand the inputs and outputs. For that, I am using one block. Hoping the white line is visible to you. White line is well visible to all of you. The white color is visible to the visible to all of you onto the board. Great. White color is well visible to this red. Okay. Now please observe here. We have a 3-bit binary code, and a 3-bit output gray code. What we want? We want to give 3-bit binary input and we want to get 3-bit output binary output gray code. Is it okay? Yes, sir. So we have 3-bit binary to gray code conversion circuit. Okay. Yes, sir. So what are the binary code I am giving? I can just give those binary codes as assigning as a variables. So I am assigning them as a variable B3, B2, B1 and B0. Okay. So B2, B1 and B0 are the input binary code, and hoping 2, 1, 0 automatically telling about the most significant bit and least significant bit. B2 is the most significant and B0 is the least significant. And the gray code we want is G2, G1 and G0. So first of all, we need to understand the relation between binary to gray code. So all of us know about the binary to gray code? Yes, sir. We want to design a circuit. For that, first of all, we have to identify the input and output relationship. First of all, we have to identify the input and output relationship. So we know about gray code and binary code. Yes, sir. Next is to construct truth table based upon the input output relation. So step number 2 says construct truth table. Truth table contains all the possibilities of the inputs and their corresponding output as well. All the possibilities of the input and the corresponding outputs as well. So we have a inputs are B2, B1, B0, and output are G2, G1, G0. Is it okay? Yes, sir. How many possibility with the 3 input bits? So total 8 possibility. Either all are low, any one of them is high, or any 2 of them are high, or all are high. So we have total 8 possibility with the 3 inputs. Is it okay? Now what you want? Sir, it indicates binary from 0 to binary of 7. 8 possibility. This is the beauty of the binary number system. Successive number shows all the possible conditions. So we have 0, 1, 2, 3, 4, 5, 6 and 7. Is it okay? Yes, sir. Now what we want? We want gray code. A gray code is a unit distance code. So a gray code is a unit distance code. So this will give you 0, 0, 0. This will give you, sir, MSB will remain as it is. These two are being XORed. So 0, 0. For 0, 0 we will get 0. For 0, 1 we will get 1. MSB will as it is 1, 1. MSB will as it is, and for different we will get 1. For different, for same we will get 0. Here MSB will as it is, for different we will get 1. For same we will get 0. MSB as it is, for different we will get 1. For different we will get 1. MSB as it is, for same we will get 0. For different we will get 1. MSB as it is, for same we will get 0. For same we will get 0. So these are the gray code. All of you able to understand in the input and output relation. What I am giving? I am giving a input binary code, and I want output as a unit distance code where each successive number will differ by only 1 bit. Is it okay? So you can observe here from 0 to 1, 1 bit, 1 to 2, 1 bit, 2 to 3, 1 bit, 3 to 4, 1 bit, 4 to 5, 1 bit, 5 to 6, 1 bit, 6 to 7, 1 bit, and 7 and 0 is also differ by only 1 bit. Is it okay? So first of all, we have to identify the inputs and outputs. Next is to construct truth table. Next step is to write output expression and minimize it. So we have total 3 outputs, G2, G1 and G0. We need to identify the logical expressions of G2, G1 and G0 and then minimize it and implement the logic circuit. So first observe G2. If you observe G2 with a B2 as a MSB and B0 as a LSB, G2 is high from 4, 5, 6, 7. G2 is high onto the binary condition of 4, 5, 6, 7, where B2 is a MSB and B0 is a LSB. So we can go with a K map to find minimized expression. B2 is a MSB, so I am writing in a SOP form, and B0 is a LSB, B1, B0, B1, B0 complement, B1, B0, B1, B0 bar. So we have 0, 1, 2, 3, 4, 5, 6 and 7. Here we are getting output logic high onto the binary condition of 4, 5, 6, 7. All of you can easily observe that it's a simple chord. So with the chord we have output G2 as B2. So output G2 is B2. Next, Next, if we observe G1, so for G1, we are getting G1 high onto the binary condition of 2, onto the binary condition of 3, onto the binary condition of 4, onto the binary condition of 5. Okay, so 2, 3, 4, 5, we are getting high onto the binary condition of 2, 3, 4, 5. Here we have considered for these numberings B2 as a MSB and B0 as a LSB. That is very important to be used on the K-map. So B2 bar B2, B1 bar B0 bar, B1 bar B0, B1 B0, B1 B0 bar. Now you can easily write 0, 1, 2, 3, 4, 5, 6, 7. Where we are getting output logic 1, beta ji? We are getting output logic 1 on 2, 3, 4, 5. So we have two pairs. With these two pairs, G2 will be, G1 will become, sir, B2 bar, from this B2 bar, and from this we have B1, plus from this we have B2, and from this we have B1 bar. So this will give you B2 XOR B1. How many of you able to understand, beta ji? In the same way, I am just observing the last part as well, that is G0. If you observe for G0, what are the conditions where G0 is high? What are the conditions where G0 is high? G0 is high onto the binary condition of 0, 1, 1, 2, 5, 6, 1, 2, 5, 6. So 1, 2, 5, 6, 0, 1, 2, 3, 4, 5, 6, 7. 1, 2, 5, 6. We have B2 bar B2, B1 bar B0 bar, B1 bar B0, B1 B0, B1 B0 bar. Where we are getting output logic high, beta ji? 1, 2, 5, 6. So we have two pairs, and with these two pairs, what is the expression for G0? We will get expression for G0, B1 bar B0 plus of B1 B0 bar, and it indicates the expression of A XOR B1 XOR B0. How many of you now able to understand? Please let me know by writing in the comment section. Is it okay? So now we have the expression of G2, we have the expression of output G1, and we have a minimized expression of output G0. To design any combinational circuit, first we have to identify the inputs and outputs. We have observed how to identify the input outputs, and we know about the relation. Accordingly, we have to construct the truth table. Then write output logical expressions and minimize it. In the last, implement the circuit, implement the logic circuit. So now we have logical expression of the outputs. Next, the last expression, last is to implement the logic circuit. So step number 4 is desired circuit implementation. Desired circuit implementation. So if you observe desired circuit implementation, it is G2 and B2 are same. So B2 and G2 are same. Okay. Then we have B1 input and we have B0 input. And you can observe that G1 is B2 XOR B1. So B2 XOR B1. Hoping all of you able to recall the gray code as well. Then for G0, we have B1 XOR B0. B1 XOR B0. How many of you able to understand this concept? Please let me know by writing in the comment section. So this is your desired combinational circuit, which is designed by you only. This is your desired combinational circuit, which is designed by you only. This is a 3-bit binary to gray code conversion circuit. Beta ji, please let me know by writing in the comment section how many of you able to understand how to design any desired combinational circuit. Can you now design any desired combinational circuit with these 4 steps? Yes. Is it okay? Can I proceed further? Yes, sir. Before moving towards a comparator, let me first tell you about the XNOR gate, because in logic gates I have covered up to XOR gate. XNOR gate I haven't covered. So please observe XNOR gate once. Okay, and then we will move towards the comparator topic. Okay, yes sir. So this is the basic part which left in logic gates. So let me cover XNOR gate here. XNOR gate. Okay. So if we talk about XNOR gate is also called as equality detector circuit. XNOR gate is also called as equality detector circuit. XNOR gate is also called as equality detector circuit. Okay. Now please observe here. In case of XNOR gate, the symbolic representation is this. This represent N over XOR. Basically, if we have AB, this shows A XOR B whole complement, or you can directly write A bar B bar plus of AB. It is represented by a circle in a dot. Is it okay? Great, sir. If we talk about switching circuit, if we talk about switching circuit for XNOR gate, then its switching circuit indicates that XNOR gate can also be defined or designed for two inputs only. XNOR gate can also be designed for two inputs only, because here we have inverted switch position. A B bar, A bar B. Whenever the lamp glows, we say output is detected as logic level 1. Is it okay? From the switching circuit, we can construct truth table for XNOR gate. So an XNOR gate will have two inputs, that is A and B, and output Y. How many possibility with the two input? 4 possibilities, sir. Either both are low, any one of them is high, or both are high. So total 4 possibility. Is it okay? Now please observe what happens for 0 0. For 0 0, what happened? A bar is 1 and B bar is 1. When A is 0, A bar is 1. When B is 0, B bar is 1. So this logic circuit, this switching circuit will got a complete path for the current to flow through the bulb, and the bulb glows. Is it okay? So output is detected as logic level 1. Is it okay? Yes, sir. Same if you observe for 1 1. What happened for 1 1? Please observe for 1 1 what happened for 1 1. If A is 1 and B is 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 1, then the circuit get completed here and the current will get this as a path. Again your bulb glows and you can say output is detected as logic level 1. So that is why it is also called as equality detector, because the output is high whenever the inputs are same. Output is high whenever the inputs are same. In case if we have 0 1, then for 0 1, if A is 0 and B is 1, if A is 0, please observe, and B is 1, then B bar is 0. Entire circuit is open at this position, so bulb will not glow and we can say output is detected as logic level 0. In case of 1 0, what happened? In case of 1 0, what happened? In case of 1, if A is 1, A bar is 0, B is 0. So entire circuit is open at this position. Again, there is no current flowing through the bulb, or you can say output is detected as logic 0. So whenever the inputs are different, XNOR gate is designed with the 2 inputs only. As per the switching circuit, XNOR gate can also be designed for the 2 inputs only. Okay. If we want a 3 input operation, then we have to design, then we have to use differently. Okay. In order to get A XNOR B XNOR C, we have to use differently. Now please observe. For XNOR gate is also designed for 2 inputs only, and with the 2 inputs, outputs are high whenever the inputs are different. Output is high whenever the inputs are same. Output is 0 whenever the inputs are different. Is it okay? So for XNOR gate, output is high only when the inputs are same. Okay. Yes, sir. Now from here we can write the logical expression. So what is logical expression? Beta ji, please observe. Logical expression of y will become, by using SOP we can write a bar b bar plus of ab. This will be indicated with a XNOR b. One very important thing, if you observe XNOR, then XNOR is a XNOR b is the same as a XOR b whole bar, but that is only true for two input. You can also write it as a XOR b whole bar, that is a XNOR b, but that is true only for the even number of input. It is not true for the odd number of inputs. That is very important thing. Is it okay? Is it okay? And that is because this function is basically this function is basically a orthogonal function. So when we talk about a orthogonal function, a XOR b is a orthogonal function where the dual and complement both are equal. Na? We will come to the orthogonal later on. So whenever the function and its dual, whenever the dual of the function and complement of the functions are same, the function is categorized as a orthogonal function. Okay. Now please observe here. So we have a XOR b whole complement same as a XNOR b. That is true for two input. Okay. But that is not true for three input. Let's have a discussion for that also. Okay. Yes, sir. One more thing. XNOR gate also follows. XNOR gate follows both. XNOR gate follows both commutative and associative law. Okay. Yes, sir. We all know about the commutative and associative law as well. One more important thing, if one input of XNOR gate is fixed, if one input of XNOR gate is fixed. So if one input of XNOR gate is fixed, it can be fixed as logic level 0 or it can be fixed as logic level 1. Okay. So please observe here, if one input of XNOR gate is fixed, then what happened? In case if one input of XNOR gate is fixed as logic level 0, then if we apply 0 onto the other terminal, same, we will get 1. If we apply 1 to the other terminal, different, this is 1 0 different, we will get 0. So for 0, it will act as a inverter. It means whatever input we are giving on this, it get inverted. Okay, if one input of a XNOR gate is fixed as logic level 1, then what happened? If one input of XNOR gate is fixed as logic level 1, if we apply 0, different, it will give 0. If we apply 1, same, this will give 1. So it means act as a buffer. Is it okay? So if we talk about XNOR gate, we have first important thing is, if we have a XNOR A, then for same we get 1. Okay. And if we have a XNOR A bar, for different it always gives 0. Okay. So these two you can just interchange to remember about buffer and inverter, just like in a XOR gate. So we have a XNOR 1 will give you a buffer, that output is A, and if you have a XNOR 0, you will get a complement. Is it okay, beta ji? So this portion is left while studying the logic gates. Okay, so here I have covered XNOR gate because in the next topic we have to use XNOR gate. Is it okay? One very important point. Please observe. See, A XOR B whole bar is nothing but A XNOR B. Is it okay? Yes, sir. If we have A bar XOR B, then what happened? If we have A XOR B bar, then what happened? If we have A bar XOR B bar, then what happened? So please observe, we can treat this as W and this as X. If we treat this as W and X, so this will become W bar X plus W X bar. Now replace W with replace W with A bar. Okay, replace W with A bar. Yes, sir. Plus B, X with B bar, X with B. Okay, yes, sir. Plus of replace W with A bar, W with A bar, and X bar, X with B, X with B. So B, we have B bar. How many of you able to understand this? Yes, sir. Now, if you observe, we have A dot B plus of A bar B bar, which is nothing but A XNOR B only. So this indicate if any one of the input will have a bubble in the XOR gate, it will act as a XNOR gate. Is it okay? The same goes for this as well. In the same way, if you observe, this will also A XNOR B. What happened in case if both will have bar? In case if both will have bar, then you all can observe this will become A B bar and A bar B. So this is nothing but it will remain same. So in a XOR gate, if all the inputs are bubbled, they will remain XOR gate only. Is it okay? If only one input is bubbled, then it will become XNOR gate. Same way, if we have A XNOR B, A XNOR B bar, okay, then this will become A XOR B. If we have A bar XNOR B, then it will become A XOR B. If we have A XNOR B bar, then also it will become A XOR B. Is it okay, beta ji? In the same way, you can do like you can just give this as W, this as X, and when you open, you will have this result. How to prove? I have given you one proof. In the same way, you can do all these. Is it okay? Yes, sir. Now please observe. Now please observe. Suppose if I have to write, A XOR B XOR C whole bar, will it be equals to A XNOR B XNOR C? No. This is very important thing. Mostly a student do this mistake that A XOR B XOR C whole bar is also A XNOR B XNOR C. This is not true. Why, sir? Let's try to make XOR gate is available with the two inputs only. So if we have a XOR gate, it will be represented like A XOR B XOR C. Is it okay? A XOR B XOR C. What you will get? A XOR B XOR C. If the entire is bar, you can put a bar here. So you can put a bubble here. You can put a bubble here. So what it become? It will become A XOR B XOR C whole complement. This is not A XOR B XOR C. A XNOR B XNOR C. This is a XOR B XOR C whole complement. Is it okay? Why I am saying this? See, if someone is thinking that, sir, can we put this bubble? Can we put this bubble here? Yes, you can put the bubble here as well. If you are going to put the bubble here, then also it will remain a XNOR gate only. Yes, sir, it will remain a XNOR gate only. XOR gate or XNOR gate only. If we put any one of the input bubbled, then it will remain XNOR gate only. Is it okay? Yes, sir. So can I put this bubble here? Then also the things will remain same. I can replace this gate with this symbol. Yes, sir. Now, if you observe, can I write like this? Can I put this bubble instead of representing here? Can I represent the bubble here? Will anyhow it will affect the result? No. So what will be your result now? Sir, we have A, B, C. So this will become A XNOR B. Is it okay? And then we have A XNOR B XOR C. How many of you able to understand? This is never going to be A XNOR B XNOR C. Because if you are considering one more bubble here, then this statement will become wrong. So these two are always not equivalent. Always remember this. So what is A XNOR B XNOR C? How can we represent A XNOR B XNOR C? How can we represent A XNOR B XNOR C? What is A XNOR B XNOR C? A XNOR B XNOR C. If we have to write A XNOR, if I want to write A XNOR B XNOR C. So XNOR gate follows XNOR gate follows A XNOR B XNOR C. Can I make like this? XNOR gate follows associative law. Yes, sir. Now, if we have this A, B, C, can I represent the same as XNOR? One more bubble here. This is also a XNOR gate only. Yes, sir. This and this are a same gate. If we have two bubbles, then we have A XNOR B XOR C. How many of you able to understand A XOR B XOR C? So it means A XNOR B XNOR C is same as A XOR B XOR C. Always remember, for odd number of inputs, they are same. However, for even number of inputs, it is a complement to each other. For even number, it is a complement, going to be complement to each other. For odd number, they are same. Is it okay? Is it okay? How many of you able to understand, Betaji? So whenever you saw like this, this is always representing A XOR B XOR C whole complement. Always remember this. So now up to this part, everyone able to understand the XNOR gate as well and their relation with the XOR gate? Great. Come back to the combinational circuit once again. How many of you able to understand, Betaji? Come back to the combinational circuit once again. I need your responses. Whenever you saw one XOR gate, one XNOR gate, that is A XOR B XOR C whole complement. Is it okay? Always remember, this is never be equivalent to A XNOR B XNOR C. This is never being equivalent to A XNOR B XNOR C. Is it okay? Always remember this thing, that A XNOR B XNOR C is same as A XOR B XOR C. Great. Now come back to the combinational circuit once again. Till now we know about the how to design combinational circuit. First we need to write the logical expression. No sir. First we need to identify the input output relationship. Next, construct truth table. Next, write logical expression and minimize it. And next, implement the logic circuit. Yes, so we can design any combinational circuit. Yes, now you are a designer. Now you can design any desired combinational circuit. Let's try to design a comparator. Let's try to design a comparator. Comparator, as the name suggests, the output is based upon the comparison of the input bits. So engineering is very organized. Every term is named such that one can easily understand its function. So now you know what is comparator. Comparator, whose output depends upon the comparison of the input bits. Simple. Yes, sir. So let's design a comparator. Let's design a comparator. Yes, Betaji, we can discuss the previous class homework as well. Now, please observe, or if you want, you can discuss the previous class homework, any homework on the Telegram channel. You can discuss all the homeworks on the Telegram channel, Varun sir PW, okay? So you can discuss all the homeworks here as well. You can just post your solution and I will let you know whether you have done correct or what the correction is needed, and also upload the actual answer as well. Okay, great. Now please observe here, comparator. It is a combinational logic circuit designed for comparison of two binary numbers. For comparison of two binary numbers. It is made by using different types of logic gates. Okay, sir. Sir, I want to first design a 1-bit comparator. What is a 1-bit comparator? First, let's talk about 1-bit comparator. So I want to design a 1-bit comparator. 1-bit comparator. How to design a 1-bit comparator, sir? In a 1-bit comparator, two 1-bit numbers, let us suppose we have two 1-bit number A and B, are compared, and depending upon the comparison, one of the output line X, Y, Z will become high. Okay? Yes, sir. So, combinational circuit for comparison of two 1-bit numbers. To design any combinational circuit, first of all, we need to identify the inputs and outputs. So let me show you the inputs and output first. We have 1-bit comparator and inputs are A, B. Output, I am using 3 output X, Y and Z. Based upon these 3 output, I can easily identify the input bits. Okay, A and B are two 1-bit numbers. Now please observe, X is high only when A is less than B or A is greater than B. Whatever you want, you can put for X. So X is equals to 1 only when A is less than B, or you can say A is greater than B. It is up to you. So I'm let us considering A is greater than B. Y is equals to 1 only when A equals to B. Whenever a number A is equals to a number B, then Y will become high. 0 otherwise. Okay, yes sir. And Z is equals to 1 only when A is less than B. 0 otherwise. So by these 3 comparison, all of you know about the A and B? Yes sir. By the 3 inputs, we can easily say what is A and what is B. Definitely if X is high, it means A is greater than B. There we have only two 1-bit numbers, so it means A is 1, B is 0. If Y is high, it means we all can see A and B both are equal. If Z is high, we all can see that A is less than B, so B is 1 and A is 0. So it's very easy to identify the input based upon these 3 output pins. Is it okay? All of you able to understand, beta ji? Great. To design any combinational circuit, first of all, we need to identify the input, output and their relationship. Now we know about the inputs. A and B are the inputs. Now we know about the outputs. X, Y, Z are the outputs. And we also know about the relationship of inputs and outputs. Next is to construct truth table. So let's construct truth table. Truth table is the table contains all the possibilities of inputs and outputs. Truth table is the table consists all the possibilities of inputs and outputs. So we have 2 inputs and 3 outputs. Okay, we have 2 inputs and 3 outputs. 2 inputs are A, B and outputs are X, Y and Z. Is it okay, beta ji? Yes sir. Now how many possibility for A? Sir, 2 possibility, 4 possibility. Either both are low, any one of them is high or both are high. So we have total 4 possibility. Either any one of them is high or both are high or both are low. Now please observe, everyone please observe, beta ji. When your X is high when A is greater than B. X is high when A is greater than B. Y is high when A is equals to B. And Z is high when A is less than B. So please observe what happened for 0, 0. For 0, 0, Y will become high. X and Z are low. X and Z are low. X and Z are low. Hello, hello. Hello. Is I am audible, beta ji? Now please observe. Sir, if change the condition X, Y and Z, it will affect in the result or not? Beta ji, it will not affect anyhow the result. X, Y and Z are just the output pins. You are a designer, so you know which pin is X, which pin is Y and which pin is Z. And you can give them the conditions. Is it okay? But yes, if you are the designer, when you are going to give that comparator to any user, you should have to tell the user as well when X is high, when Y is high and when Z is high. Because he don't know, he just can see that 3 pins are coming. Is it okay? Yes. Now I am hoping all of you able to understand. Now please observe for 0, 1. For 0, 1, what happened? For 0, 1, which will become high? Sir, B is greater than A. B is greater than A. So B is greater than A. B is greater than A. B is greater than A. For 1, 0, A is greater than B. And for 1, 1, Y is high. Both are low. Now, we know how to fill the truth table now. First of all, we have to identify the input-output relationship. Next is to construct truth table, write logical expression. Next is to write logical expression. So what is the logical expression? Can you please tell me what is the logical expression for X, beta ji? Logical expression for X. Logical expression for X will become A bar B. Logical expression for Y will become A XNOR B. And logical expression for Z will become A B bar. For X it is A B bar and for this A bar B. Please do the correction, beta ji. So for Z we have this one, that is A bar B, and for this we have A B bar for X. So please do the correction of X and Z. Okay, rest everything is okay. Now next is to implement the logic circuit. How to implement the logic circuit? Very easy, sir. We have to implement A bar B. So we need one AND gate. Then we need one XNOR gate. And then we need one more AND gate. Okay. Yes, sir. So it can also be represented by A XOR B. Na? We can further reduce it. We have A bar B, A B bar and XNOR. So either you can utilize this result to find XNOR or you can create XNOR alone. So let me create a XNOR and A B bar, and we have A XNOR B, and we have A bar B. So X, Y and Z. This is your desired combinational circuit. So in this way you can design any desired combinational circuit. What we have to do? Write the logic. First of all, we have to identify the inputs and outputs. Next is to construct truth table, write logical expression, minimize it and implement the logic circuit. So now we have a 1-bit comparator. Can you design a 2-bit comparator as well? How many of you can design a 2-bit comparator as well? Please let me know by writing in the comment section, beta ji. How many of you can design a 2-bit comparator as well? How many of you can design the 2-bit comparator? Presently we have 1-bit comparator. All of you able to understand this 1-bit comparator? Great. Let's design a 2-bit, 3-bit and any number of bits. Yes, sir. So let's have a 2-bit comparator now. So in a 2-bit comparator, please observe, beta ji, in a 2-bit comparator, we have, in a 2-bit comparator, we have a number A and B. Each A and B are a 2-bit numbers. A and B are 2-bit numbers. So we have A2 or A1, A0, A1, A0 and B1, B0. So we have total 4 bits as a input bit. We have 2 numbers A and B. Each A and B are a 2-bit numbers. Is it okay? A and B are a 2-bit numbers. A is a 2-bit number, B is a 2-bit number. Based upon that, we have to observe whether A is greater than B, A is less than B, or A is equals to B. So this is high, this is high, only when A is greater than B. This is high only when A is equals to B, and this is high only when A is less than B. Can you tell me the logical expression for X, Y, and Z now? Sir, we have total 4 bits. A2, A1, A0, B1, B0. So total number of possible combination will be, sir, 16, from binary of 0 to binary of 15. Is it okay? Yes, sir. So total combination will become 16. How many of you able to understand? Now for each we have to observe. For each we have to observe. For each we have to observe. Is it okay? Yes, sir. But we have one more approach. Please observe the shortcut approach as well. One approach is we can go with a binary of 0 to binary of 15, that is 0, 0, 0, 0 to 1, 1, 1, 1. If we are going to write from binary of 0 to binary of 15, total 16 combination, and we see where A is greater than B, we are getting, and then we can use K-map to find the minimized expression, and then we can implement. Instead of going with this long method, let's go with the very short method. So we have two numbers, okay? We have two numbers A and B. Let's have a shortcut. Okay, please observe. Let's discuss about the shortcut. So we have a number A and we have a number B. A number will be 0, 0. A number will be having A1, A0, and B number also having B1, B0. So A will be 0, 0, 0, 1, 1, 0, and 1, 1. B number is 0, 0, 0, 1, 1, 0, and 1, 1. All of you can see this? Yes, sir. Now please observe, what is the logical expression for X? So I am directly writing the logical expression. Instead of going with the truth table and finding the minimized expression, we can utilize the 1-bit comparator information to write the logical expression of 2-bit, 3-bit, and n number of bits. Now please observe here, what is the logical expression for X? Please observe, X is high only when A is greater than B. A is greater than B. Now please observe here, in case if A1 is greater than this B1, in case if A1 is greater than B1, in case of a number A, MSB A1 is greater than MSB B1, then A must be greater than B. We all can see this is the binary of 0, binary of 1. We all can see this is the binary of 0, binary of 1, binary of 2, or I am just writing here. We all can see this is the binary of 0, binary of 1, binary of 2, binary of 3. Is it okay? In the same way, we all can see this is the binary of 0, binary of 1, binary of 2, binary of 3. So if A1 is high, this is 2, 2 is greater than 1, 2 is greater than 0. How many of you can see this? Yes, sir. So you can say, sir, if A1 is high and B1 is low, definitely your X will become high. A1 is the MSB of A number, B1 is the MSB of B number. If A1 is high, then B1, definitely your X is high. In case if A1 and B1 are equal, in case if we observe this 2 and 3, so in case if A1 is equals to B1, XNOR gate output is logic 1 whenever the two inputs are same. So in case if A1 is equals to B1, in case if the MSBs are same, 0, 0, or you can say 1, 1, if the MSBs are same, then next significant bit A0, A0 if greater than B0, A0 if greater than B0, please observe, if A1 and B1 are same, if A1 and B1 are same, if A1 and B1 are same, A0 and B0 are same, then we have only Y going to be high. But in case if A1 and B1 have same MSBs, A1 and B1 have same MSBs, but A0 is greater than B0, A0 is greater than B0, then also your A is greater than B. Yes, sir. So if A1 and B1 are same, but A0 is greater than B0. A0 is greater than B0. Then also your X will become high. So we can write the logical expression for X as A1 B1 bar plus of A1 XNOR B1 dot multiplied with A0 B0 bar. Now you can put any condition. X is going to be only high when A is greater than B. Is it okay, beta ji? Is it okay, beta ji? Please tell me by writing in the comment section. Yes, sir. Number A is greater than B. Number A is greater than B. Either the MSB A1 is greater than MSB B1. In case if MSBs have equal, then LSB of A number must be greater than LSB of B number. Then also your number A is greater than number B. Is it okay? Suppose if we have this number and this number. So in this number, MSBs are same. A1 and B1 are same. But A0 is greater than B0. Then also your A1 is greater than B1. If you observe in this case, MSBs are same. MSBs are same here. MSBs of this number and MSB of this number is the same. But you all can see here LSB A1 is greater than LSB B1. Then also your A is greater than B. How many of you able to understand how I have write the expression of X? In the same way, can you write the expression of Y as well? What is the logical expression for Y? Logical expression for Y, sir, A1 B1 must be equals to A2 B2. A1 B1 and A2 B2 must be equal. So A1 XNOR B1 as well as A0 XNOR B0. When both these conditions satisfied, then only your output Y will become high. If any one of the condition is not meeting, your Y will remain low. Is it okay? Yes, sir. Now please observe the last one. Last one, that is logical expression for Z. If you observe what is the logical expression for Z, beta ji? Please observe logical expression for Z. Z is high when A is less than B. A is less than B means B means first, in case of A1 low but B1 high, we will get Z high because that indicate number B is greater than A. If A1 and B1 are equal, then LSB of A number must be less than LSB of B number. How many of you able to understand to write the logical expression of 2-bit comparator directly? Is it okay? Yes, sir. How many of you able to understand? Please let me know by writing in the comment section. One very important note point. Please observe. Let A number is of n bit and B number is of n bit. Okay. Then total number of possible combination is total number of possible combination. Suppose if we have a number of 2-bit, then how many possible combination? We all can see 0, 0, 0, 1, 1, 0, 1, 1. 4 combination possible. For 1 bit, 2 combinations are possible. Similarly, for 3 bit, 8 combinations are possible. So for n bit, 2 to the power n combinations are possible. Is it okay? In the same way, B number of n bit, then total number of possible combination for number B is, sir, in the same way 2 to the power n. So if we have A and B two numbers comparator, then 2 n bit number comparator will have possible combination, how much beta ji? Sir, 2 to the power n into 2 to the power n, that is 2 to the power 2n combination possible. Is it okay? Yes, sir. Total number of equal combination possible. Total number of equal combinations. How many number of equal combinations? If we have 2 bit, if we have 1 bit, we have observed if we have 1 bit comparator will have how many number of combination possible? Equal 2 combination. Okay. For 2 bit we have 4 combination possible. 1, 2, 3, 4, where A number and B number are equal. In the same way for n bit we have 2 to the power n combination possible. Is it okay? Sir, for 2 bit we have 2 combination. For 1 bit comparator we have 2 combination possible. For 2 bit we have 4 combination possible. For 3 bit we have 8 combination possible. So for n bit we have 2 to the power n combination possible. If we talk about total number of unequal combinations. So total number of unequal combinations will become 2 to the power 2n is the total number of combination by minus 2 to the power n combination. So total number of A greater than B or B greater than A or A less than B possible combinations. If we talk about this, then this is the total number of unequal combination. If we divide it by 2, because half we have A greater than B and half of the number of possible combination unequal where A less than B. So total number of possible combination of A greater than B or A less than B will be equals to 2 to the power 2n minus 2 to the power n divided by 2. How many of you able to understand beta ji? Please let me know by writing in the comment section. Great. So now we can have a n bit combination. There is no issue. We can have a n bit comparator. There is no issue. How many of you able to understand? Sir, can you please explain in Hindi as well? Beta, it's a gate Wallah English channel and this series is designed for English, but I am using very simple language. If you just listen, you can understand everything, yaar. You are an engineer. I am using the very basic language. Very basic language you can easily understand. Still, if you have any doubt in anything, please just let me know. I will repeat it in Hindi as well. There is no issue. Okay. Great. How many of you able to understand? Great, sir. Great, sir. Can I move ahead? Can I move ahead? Yes, sir. Suppose if we have let's try to solve one question asked in GATE. Okay. Now please observe here. Please observe this question. Please observe this question. Let x, x1, x0, y, y1, y0 be unsigned 2-bit numbers. Unsigned means only the magnitude is represented by the binaries. Okay. So unsigned 2-bit numbers. The function f is 1 if x is greater than y. If x is greater than y, and function f is 0 otherwise. Function f is 1 if x is greater than y and f is equals to 0 otherwise. The minimal SOP product expression of f is, can you write the minimal SOP product of minimal sum of product expression for f? Can you write minimal minimized sum of product expression for f? Yes, sir. How to write? Sir, we all can see we have a two numbers x and y, where x is greater than y. Is it okay? Yes, sir. X will have two numbers, x1, x0. Y is also of two numbers, y1, y1, y0. So since we have to find the minimized expression, we know about the modified expression. We can easily write the modified expression. But since we have to find the minimized expression, can you write the minimized expression as well? Yes, sir. How? Please observe. We have a logical expression. We have a logical expression of the function f as x is greater than y. So x1, y1 bar plus of x1 XNOR y1. So in case if the MSB is high, if the MSB are equal, then LSB x must be greater than LSB y. Is it okay? Yes, sir. But we have to open this to find the minimized. So x1 y1 complement plus of x1 y1 complement plus of x1 y1 complement plus x1 y1 multiplied with x0 y0 complement. So actually we have x1 y1 complement plus of x1 complement x0 y1 complement y0 complement plus of x1 y1 x1 x0 y1 y0 complement. Is it okay? Now we can use K-map to find the minimized logical expression. So how to find the minimized logical expression, beta ji? We can use the K-map to find the minimized logical expression. Okay. Yes, sir. If you observe here, we have the number with the x1 as a MSB. So x1 bar x0 bar x1 bar x0 x1 x0 x1 x0 bar y1 y0 bar y1 bar y0 y1 y0 y1 y0 bar. So we have a number 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 and 15. What are the binary positions where we are getting output logic high? We all can see if x1 is greater, even you can put here as well. Since x1 is greater than y1, in case x1 is greater than y1, in case if x1 is greater than y1, definitely your output is high. So x1 y1 complement is a chord. And how you will get chord? X1 from here and y1 complement you will get from here. So if x1 is greater than y1, definitely we are getting output logic 1. This is a chord. So chord will have this x1 and from here y1 complement. Is it okay? This also we are learning how to get the minimized expression for any Boolean function given. You can have a minimized by using K-map of any Boolean function given, because there is a possibility more than one minimized expression in the SOP. Is it okay? Now we have x bar, x1 bar, x0, x1 bar, x0, x1 bar is from here, x0, y1, y0 bar. So we are talking about 4 and x1, x0, already x1, x0 is here, y1, y0 bar, y1, y0 bar. Is it okay? Please observe. So beta ji, we have this chord in the minimized expression and we have two pairs. One pair is possible, this one, okay, and one pair possible is this one. How many of you can observe this? And now you also know how to identify the minimized expression for any given Boolean expression. Is it okay? Yes, sir. So now please observe. First we have x1 y1 complement. So we have f function f minimized expression for the function f is x1 y1 complement. Is it okay? Yes, sir. And then we have this pair which gives x0 y1 y0 bar, x0 y1 x0 y1 y0 y1 complement y1 complement y0 complement plus of we have, sir, x1 x0 and from here we have y0 complement, x1 x0 y0 complement. How many of you able to understand the minimized expression for the given function as well? How many of you now able to understand the given function as well? What I am able to see is most of you are started losing your interest, and why I don't know. Can you please tell me why you are losing the interest? How many of you able to understand up to this part, Bitaji? This is very easy, yaar. How to design any desired logical, how to design any desired combinational circuit? First, we need to write the logical first we need to understand the input-output relationship, construct truth table, write logical expression and minimize it, implement the logic circuit. I am doing the same thing. We have learned so far comparator. Comparator is used to compare two binary numbers. They may have equal number of bits or unequal number of bits. How many of you able to understand up to this part? Is it okay? Great, sir. Can you please tell me if A is 5-bit number and B is 2-bit number, then find number of combination for A greater than B. Find number of combination for A less than B. Find number of combination for A less than B. Can you tell me how many number of combination for A less than B? Can you tell me how many number of combination for A less than B? Sir, actually we have 5-bit will become little bit more. Let me take first in order to explain you 3-bit. Okay. So suppose A is a 3-bit number and B is a 2-bit number. Okay, because 5-bit will have lot of number of combinations. 32 up to goes to it is going up to 32. So it will be easier to understand with 3-bit and 2-bit. Okay. So if we have a 3-bit and if we have a 2-bit number B, then for how many combinations A is less than B? How to solve this? Please observe, Betaji. We have a number A and we have a number B. Okay. Yes, sir. We have a number A and we have a number B. In case of A, how many possibility we have? A2, A1, A0. We have total possibility of 0. So 0 is the binary of 0, 0, 0. Then 1, 2, 3, 4, 5, 6 and 7. So total possibility is 8. And we have a number B, a 2-bit number. So basically 2-bit number is B1, B0. So here we have a binary of 0, 1, 2, 3. For a 2-bit number, maximum we can go up to binary of 3 only. Is it okay? Yes, sir. Now please observe, we have to identify for how many combination B is greater than A. How many combination B is greater than A? Now please observe here. B is greater than A. How many combination for B is greater than A? Please observe, if this is 0, they are same. If this is 1, then how many possible combination for which B is greater than A? Only one combination is possible. Only one combination is possible. If B is 2, then how many combinations are possible? If B is 2, then how many combinations are possible where B is greater than A? Sir, 2 combinations are possible. Is it okay? If B is 3, then how many number of combinations are possible for B to be greater than A? Sir, 1, 2, 3. 3 combinations are possible. Now, after that, sir, either A will become greater than B or A will become equals to B. But there is no other possibility where B is greater than A. So total how many number of combinations possible for B greater than A? Okay, in the same way, how many possible combinations for How many possible combinations for A equals to B? If we talk about A equals to B, then how many possible combination? Sir, 1, 2, 3, 4. The lower number of bits number. The lower number of bits number. Is it okay? So how many possible combination for the lower number of bits number? Sir, for the lower number of bits number, we have total 4 combination possible. So for 4 combination, A is becoming B. A equals to B. 0, 0, 000 and 00, 000 1, 001 and 01, 002 and 00, 0010, and here 10, and here we have 00, sorry, 0, 11, and here we have 11. Is it okay? So how many possible combination? 4. In the same way, if we talk about A greater than B, so for A greater than B, how many possible combinations? Sir, whenever we have the A higher number, we always go with the B and equal. Then total number of combination minus the addition of these two will be the answer. So how many possible combination for 3-bit? Sir, 8 combination, from binary of 0 to binary of 7. 8 combination. So for 8 combination and for 2 combination. So this will become 8 combination of this and 2 combination of this. So how many combination total will become? Sir, total number of bits will become 2 to the power 5. 2 to the power 5 means 31. Out of 31 combination, 10 combinations are this. So remaining combination will become, remaining 21 combination will become this. Let's try to understand again. For how many combination A is greater than B? Now please observe. For this we have one combination possible. For this we have one combination possible, that is A having 1 binary of 1 and B having binary of 0. So one combination. For this we have 2 combination possible, that is A binary of 1 and binary of 2. Sorry, A having binary of 2 and B having binary of 0, binary of 1. If A is a binary of 3, then B having binary of 0, binary of 1, binary of 2. If A having 4, then binary of 0, binary of 1, binary of 2, binary of 3. So 4 combinations possible. Then, sir, for all, now only we have 4 combination possible. Is it okay? Yes, sir. 4 combination possible. Because we don't have more than 4 combination for this. Is it okay? Even for 5 we talk, then we have binary of 0, binary of 1, binary of 2, binary of 3. Only 4 combinations where A is greater than B. Same for 6 as well, same for 7 as well. So how many total number of combinations going on? Sir, we have so 16, 17, 16, 20, 22. So total 22 combinations we have where A is greater than B. Total number of combinations are 32. I am sorry. 3 plus 2, it will become 5. So 0 to 31, total number of combination will become 32. Is it okay? Out of 32 combination, 10 combination we have this. So 22 combination, A is greater than B. How many of you now can solve any question based on the comparator? This is a very important topic, especially for 2027. Is it okay? Please let me know by writing in the comment section, beta ji. I have made this very easy. I have made this very easy. So from now onward, you can easily solve for any number of bits. Can you find for 5? If A is 5 and B is 2, can you find? Yes, sir. We will start with a lower number. First find the lower number higher, then equal, and then we can subtract from the total. Easy? Yes, sir. Yes, beta ji, this is a full course. How many of you able to understand up to this part? Please let me know by writing in the comment section, beta ji. Great. So now we have a complete information related to a n-bit comparators. Maybe A and B have different number of bits. That is, there is no issue. Now we know about the comparator. Next, please write down adder. In adder, first of all, we will see half adder. I am interested to design a adder circuit. I am interested to design a adder circuit. Adder circuit is also a combinational circuit. Is it okay? So let's talk about half adder first. So in general, how a half adder circuit will work? Half adder circuit, it is a combinational circuit that performs addition of two 1-bit numbers. That performs addition of two 1 bit numbers. Okay, that performs addition of two 1 bit number. And provide sum and carry. How many of you able to understand, Betaji? Great. So we have a combinational circuit we want to design. Actually, we want to design a combinational circuit which performs addition of two 1 bit numbers. It will give a sum bit and provides a carry bit in case if there is any carry. Is it okay? So first of all, for designing any desired combinational circuit, we need to understand the input output and their relation. So we know the inputs are A and B, and one output is a sum bit, another output is carry. Whenever carry is high, we have output high. So now we know about the input and output. Next is to construct truth table. So let's construct truth table. Please observe, Betaji. So let's construct truth table. In truth table, we have A and B. In truth table, we have A and B. Please observe, inputs A and B and outputs are sum and carry. Outputs are sum and carry. Now please observe, we have total 4 possibility for the two input AB. Either both are low, any one of them is high, or both are high, which can be represented in the form of binary of 0, binary of 1, binary of 2, binary of 3. If we talk about outputs, then we have a carry and sum. We have outputs, carry and sum. So here we have input and output. These are the inputs. This is your output. Now we all know how to find sum. What is 0, 0 in a binary? What is 0, 0? 0 plus 0 will give 0. There is no carry going on, so carry will remain low. Carry will become high only if there are high carry. 0, 1, if we add 0, 0 plus 1, 0 plus 1 is 1 only, and carry will remain 0. 1 plus 0 is also 1 only, carry remains 0. What is 1 plus 1? 1 plus 1 will become 2. But in base 2, we will write 1, 0. So sum will become 0 and carry will become 1. So when we add 1, 1, it will become 0 carry over 1. Is it okay? How many of you are able to understand this? Whenever we are going to add 1, 1, in 1 bit, the sum bit will become 0 and carry bit will become high. Is it okay? Yes, sir. To design any combinational circuit, first of all, we need to identify the input outputs. Next is to construct truth table. Then write logical expression. So what is the logical expression for the sum and carry? We all can see logical expression for sum will become, we have A bar B, that is 0. Let me represent in this way as well. Summation of M 1 comma 2, or it can be represented in the form of A bar B plus AB bar, which will be represented as A XOR B as the minimized expression. In the same way, if we talk about carry, then what is the carry? Carry will become summation of 3, summation of M3, that will be represented as A dot B. Next is circuit implementation. So can you implement this circuit? Yes, sir. We need one XOR gate. We need one XOR gate. Okay. And we need one AND gate. So if we have one XOR gate and one AND gate, one XOR gate and one AND gate, the sum and carry is available to us. So this is how we can design any desired combinational circuit. You are the one who has designed this circuit of adder. How many of you able to understand up to this part, Betaji? How many of you able to understand up to this part, Betaji? Please let me know by writing in the comment section. Great. So half adder contains one XOR gate, one AND gate. Is it okay? Yes, sir. One very important point that always remember, that is number of NAND. number of NAND or NOR gate required for half adder is equals to 5. Is it okay? If you want to design a half adder by using only XOR gate, by using only NAND gate, I'm repeating my words. If you want to design a half adder by using only NAND gate or by using only NOR gate, then number of NAND or number of NOR gate required will be equals to 5. Is it okay? Great. How many of you able to understand up to this part, beta ji? I have also shown you about the number of NAND gate. Is it okay? Please observe. Number of NAND gate required to implement a half adder. So a half adder required A XOR B. A XOR B can be represented here as A B. Is it okay? Yes, sir. So we get A bar let me modify a little bit, otherwise maybe you have confusion. This is basically crossing like this. Okay. Yes, sir. So we have basically A dot B whole bar, and again when we pass it, we have a carry. Carry is AB. Is it okay? And we have a AB bar, and this will be acting as a bubbled OR gate. Okay. So before going to bubbled OR gate, you can just observe here. Here we have A dot A bar plus B bar whole bar, and here we have B bar B dot A bar plus B bar whole bar. Okay. So actually what is the information going here? Sir, this will be acting as a bubbled OR gate. This will be acting as a bubbled OR gate. Whenever I see this NAND gate, it will look to me as a bubbled OR gate. Is it okay? So this bubble is going to cancel out this part. Is it okay? Yes, sir. And OR operation will perform. So when you open this, what it become? Sir, A bar will become 0, and we have A dot B bar, A dot B bar and A bar B. So we will get here A bar B plus A B bar, and that is nothing but A XOR B only. Is it okay? So in this way, we can have the implementation of half adder by using NAND gate only. In the same way for the NOR gate as well. In the same way for the NOR gate as well. So we have this A bar here available, B bar, and here we have A plus B whole bar, which can be represented as A bar, B bar. Basically, this is the condition. So we have A bar, B bar. When they are going to be passed through the bubbled AND gate, it looks to me as a bubbled AND gate. It looks to me as a bubbled AND gate. So this bubbled AND gate will cancel these bars, and we have a carry. Carry is A dot B. Is it okay? And as well as we have A dot B here, and we have A bar, B bar here. Is it okay? Yes, sir. And we all know this is a NOR gate. So a NOR gate is representing A XNOR B whole complement, because we have AB bar. So that is A XOR B only. That is sum. So we can have the 5 NAND gate or 5 NOR gate is required. I have also shown you what is the arrangement for implementation of a half adder circuit. They are not going to ask you about the arrangement. In objective, they can't ask about the arrangement, but maybe if the circuit is given to you, how you have to approach to find the output, that I try to show with this example, that I am able to see the NOR gate as a bubbled AND gate or a NAND gate as a bubbled OR gate. Is it okay? Hoping all of you able to understand up to this part. Is it okay? Great, sir. Now let's talk about full adder. See, whenever we are going to perform the addition of two numbers, now two numbers are never be only in one bit. They are of n number of bits. Actually, suppose if we have to perform addition of 10, or say addition of 6 and addition of 7. If you want to perform this, what is the binary of 6? Sir, binary of 6 in 4 bit is, let us suppose in 4 bit, so 0 1 1 0. And what is the binary of 7? So 7 in binary is 0 1 1 1. So we are not interested to perform the addition of these 2 bit. We are actually concerned to do the addition of number of bits. Then only we can perform actual addition of a bigger numbers. Is it okay? Yes, sir. So if we have a half adder, we can do the addition of 2 bit. But when we are going to add these 2 bit, we will get some bit. Is it okay? We will get some bit and we get some carry bit. Now we have 3 bits. So how to do the addition of these 3 bit? For that, it will be better to go with a full adder. So in full adder also, we are performing the addition of 2 numbers only. One is a carry bit which is going to add. Is it okay? But for simplicity, we keep it like 3 1-bit number. It is an addition of 3 1-bit numbers. Is it okay? For simplicity, I am keeping it very simple. Like full adder is a combinational circuit to perform addition of 3 1-bit number. Is it okay? Actually, it is a 2 1-bit number. One carry is coming. But in order to make it very simple, I am just keeping it 3 bit. It is the addition of 3 1-bit numbers. Is it okay? Yes, sir. Now I am hoping all of you able to understand also why we need full adder. Please observe here. Please observe here. Full adder. Full adder is a combinational circuit. Full adder is a combinational circuit to perform addition of 3 binary digits and provide sum and carry. So we have 3 input bits A, B, C, and we have sum and carry output. How many of you able to understand up to this part? Okay. So a sum, logical expression may be different, but arithmetically what we have to do, A plus B whole is going to be added with C. A plus B whole plus C. This is arithmetic function need to be done. If carry will become high, we make carry high. If the carry will remain low, we will make carry low. Is it okay? Yes, sir. So now please observe here. Once you know about the input and output, to design any combinational circuit, first of all, we need to construct the, we need to identify the inputs and outputs and their relationship. Next is to construct truth table. So let's construct truth table now. Please observe, beta ji. We have a 3 bit. So how many possibility with a 3 bit? Sir, total 8 possibility, which can be represented from binary of 0 to binary of 7. Yes, sir. So we have a 3 input bit A, B, and C. I know I am moving very fast, but the reason is this is very easy topic. All of you are getting everything. So I am moving little bit fast so that I can cover more and more subject. Is it okay? Is it okay? Yes, great. But you need to write in the comment section as well. Then only I will be able to understand that you are getting the things. Great. So we have A, B, and C. And what is the output? Sum bit and carry bit. So sum bit, and I'm using one more for the carry as well. Let me write the carry here only. So sum and carry. Is it okay? Yes, sir. So we have 0, 0, 0, binary of 0 to binary of 7. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 6, and 1, 1, 1, 7. It can be indicated with a binary of 0, 1, 2, 3, 4, 5, 6, and 7. How many possibility? Sir, total 8 possibility that can be represented from binary of 0 to binary of 7. Is it okay? Can you fill the output? Sir, we have to arithmetically we need to perform A plus B whole plus C. To find sum, arithmetically we need to perform A plus B whole plus C. This is not the logical expression. We need to perform this mathematical operation. Okay, yes sir. And when the carry will become high, we put carry high. So please observe, a plus b, 0 plus 0, first you need to perform a plus b, 0 plus 0, 0 plus 0, 0, carry over 0. How many of you able to understand? Again, please observe, 0 plus 0, 0, plus 1, 1, carry over 0. Again, please observe, 0 plus 1, 1, 1 plus 0, 1, carry over 0. Again observe, 0 plus 1, 0 plus 1, 1, plus 1, 0 plus 1, 1, 1 plus 1, 0, carry over 1. How many of you able to understand, beta ji? 1 plus 0, 1, plus 0, 1, carry over 0. 1 plus 1, 1 plus 0, 1, 1 plus 1, 0, carry over 1. 1 plus 1, 0, 0 plus 0, 0, carry over 1. 1 plus 1, 0, carry over 1. 1 plus 1, 0, 0 plus 1, 1. How many of you able to understand how to write the logical, how to write the truth table for the full adder? So this is a truth table for the full adder. You are a designer, beta ji. You are designing this full adder circuit now. So we have sum bit and carry bit, sir. We have a sum bit and carry bit, sir. What is sum bit? Sum bit is summation of m. What are the binary conditions where we are getting output logic high of sum bit? 1, 2, 4, 7. 1, 2, 4, 7. This number will come very frequent. Always remember 1, 2, 4, 7. This number will come very frequent. Whenever it is in the form of summation of min term 1, 2, 4, 7, it is always A XOR B XOR C. Let me prove it as well. So what is 1? Min term of 1 will be A bar, B bar, C. Plus min term of 2 will be A bar, B, C bar. Min term of 4 will be A, B bar, C bar. Min term of 7 is 1, 1, 1, A, B, C. Is it okay? 4 binary is 1, 0, 0. So I have represented A, B bar, C bar in this way. You can easily write. Now please observe. To find the minimized expression, first of all, please observe. Can we have a C common from first and last? Can we have a C common from first and last? If we take C common from first and last, then we have A bar, B bar plus of AB, which can be represented as A XNOR B. So can I write A XOR B whole complement as A XNOR B? Plus of, if you observe second and third, we have a common C bar and remaining will be A bar B plus A B bar. So A XOR B. How many of you able to understand this from second and third? Now, if you are able to get up to this part, please see, beta ji, from first and last we have C common. Inside the brackets we have A XNOR B, which can be represented as A XOR B whole complement. Is it okay? And second and third we have C common. If we have observed the inside the bracket, it will be A bar B plus A B bar, which can be represented as A XOR B. Now if we take, let x to be equals to A XOR B. So actually we have a function C x bar plus C bar x, which can be represented as x XOR C, because XOR gate follows XOR gate follows commutative law. So either you can write C XOR X or X XOR C, both are the same thing. Now we can replace this X with A XOR B XOR C. How many of you able to understand, beta ji, up to this part? The sum of a full adder will have a logical expression A XOR B XOR C. One very important thing, whenever we talk about XOR gate, it is always an odd number of ones detector circuit. XOR gate is a odd number of ones detector circuit. So logical expression is the same as 3-bit odd number of ones detector circuit. Why I am writing this? Please observe. if I say to you, design a combinational circuit which gives output logic 1 whenever the number of ones in an input is an odd number. Number of ones in an input is an odd number. So you will design like this. Number of ones in an input is an odd number. So we have A, B, C input. In this, only 1 is logic level 1. So we will have logic level 1. Only 1 out of 3 is 1. So 1. 2, even number. Even number of ones are high, 0. Even number of odd number of ones are high, odd number of ones 1. Even number of ones are high, 0. Even number of ones are high, 0. Odd number of ones are high, 1. So the logical expression of 3-bit odd number of ones detector circuit is also A XOR B XOR C only. How many of you now able to understand? Great. Now please observe the carry. Carry is very important. The logical expression for carry. Carry we are getting high onto the binary conditions of 3, 5, 6 and 7. 3, 5, 6 and 7. Can you observe, if we want to design the logical expression for a majority bit detector circuit, a 3-bit majority detector circuit, whenever a majority bit is 0, we will get 0. Majority bit is high, we will get high. So if you observe here, majority bit detector circuit, majority of 0, we get 0. Majority out of 3, majority is of 0, we are getting 0. Majority is of 0, we are getting 0. Majority is of 1, there are 2 1 and 1 0, so we are getting 1. Majority is of 0, we are getting 0. Majority is of 1, we are getting 1. Majority is of 1, we are getting 1. Majority is of 1, we are getting 1. So carry logical expression of a full adder will have same logical expression as that 3-bit majority detector circuit. So can I say this? Logical expression is the same as 3-bit majority detector circuit. How many of you able to understand, Betaji? The logical expression of a carry bit is same as the logical expression of 3-bit majority detector circuit. So where the majority of bits at the input is same as the output. Is it okay? Yes, sir. Now please observe, this is not the minimized expression. We need minimized expression before implementing the function. So let's have a minimized expression for the carry. What is the minimized expression for the carry? For that we may go with the K-map. So let's use K-map to find the minimized logical expression for carry. Is it okay? Yes, sir. Now please observe, for carry we have a function 3, 5, 6, 7 where majority is high. Majority is high. Is it okay? Yes, sir. Now please observe. So out of A, B, C, A is a MSB for this 3, 5, 6, 7 numbers. A is taken as a MSB and C is taken as a LSB. So keeping that in mind, we have A bar A, B bar C bar, B bar C, B C, B C bar. Now we have the numbering 0, 1, 2, 3, 4, 5, 6 and 7. Where we are getting output logic high, Betaji? We are getting output logic high onto the binary of 3, 5, 6 and 7. Great. So we have total 3 combinations of pair. And if we observe the pairs, we have carry logical function as AB plus BC plus AC. How many of you able to see this? AC, AB and BC. How many of you able to understand this? Yes, sir. So this is very important function. If you want to implement a carry function, then minimized expression is this. And also do the note point here. Carry of full adder is a self-dual function. We'll discuss the dual, self-dual, how to check the dual functions and all in the upcoming lectures. But right now, just write down here and remember the self-dual function, that carry output of a full adder is a self-dual function. How many of you able to understand up to this part, Betaji? Great, sir. Can we implement? Yes, sir, we can implement. Let's implement A, B, C. So we have circuit implementation. We have three inputs A, B, and C. Can we design a 3-input XOR gate? No, sir. We can't design a 3-input XOR gate. Why, beta ji? Because of its switching circuit. We can only have a 2-input XOR gate. So in order to have A XOR B XOR C, what we have to do? A XOR B XOR C, what we have to do? We need 2 XOR gates. We need at least 2 XOR gate to implement A XOR B XOR C. We can't design a 3-input XOR gate. Is it okay? Even if we are designing a 3-input XOR gate, this is what the meaning is. So we have A XOR B XOR C. We have A XOR B XOR C. Some function will be implemented. Now let's talk about carry. So carry will have AB plus BC plus AB plus BC plus AC. So we need 3 AND gate, 1, 2, and 3. And we need 1 OR gate. So if we are performing AB plus BC plus, so we have AB. Is it okay? Wherever this dot is darked, it means it is connected. And this means it is overlapping. Is it okay? Yes, sir. AB plus BC plus AC. So we have AC as well. And we have BC. How many of you able to understand up to this part? Please let me know by writing in the comment section, beta ji. AB, AC, BC. This is your carry. How many of you able to understand up to this part? Please let me know by writing in the comment section. This is very important. Now in a full adder, we will came to know one thing, that in case if all the logic gates will have a delay of TPD, then minimum time delay required to get some bit is 2 TPD and to get carry bit is also 2 TPD. 1 TPD time is required for this level, another TPD time is required for this level. So if each logic gate in full adder will have a propagation delay of TPD, which is not actually happened, because of the switching circuit of XNOR gate will have always more delay comparative to the basic gate, even if the basic gate will have a higher number of inputs. Is it okay? Because of the switching circuit, XNOR gate or XOR gate will always have a higher delay comparative to the basic gate. If we assume that all the logic gates will have a delay of TPD, if we assume, then what is the minimum delay time required? What is the minimum time delay required to have a carry bit and some bit of a full adder available? That will be equals to 2 TPD time. If you are watching the output carry or sum before 2 TPD, definitely you are getting wrong. In an actual practice, XOR gates will have more delay comparative to the basic gate. So maybe it will have 1.5 TPD and this will have TPD. So what happened under that condition? 1.5, 1.5. It means sum will be available after 3 TPD. However, carry will be available after 2 TPD. Is it okay? Yes, sir. Now I am hoping all of you able to understand up to this part. Please let me know by writing in the comment section, beta ji. Great. When we engineers saw this, we are very curious to reduce the cost and to increase the speed. What is the cost? If each logic gate will have a delay of a TPD, then the minimum delay will be 2 TPD. But in actual practice, XOR gates will have more delay comparative to basic gate. For a moment, if we assume XOR gate delay is twice of the basic gate, then carry will be available after 2 TPD and sum will be available after 4 TPD. Is it okay? 2 TPD for this XOR gate and 2 TPD for this XOR gate. Is it okay? Yes, sir. What is the cost, sir? 1, 2, 3, 4, 5, 6. 6 logic gate cost will come to design this full adder. Is it okay? Yes, sir. At this time, some engineers start thoughting, can we reduce the cost? with the same delay. Okay. And with this thought, he started writing modified carry expression. Is it okay? Great, sir. So minimized we have AB plus BC plus CA. That is the minimized. Now let's talk about a carry expression once again. What is the carry expression? We have a carry expression summation of m 3765 3567. So in terms of ABC, we can write A. 3 can be represented as A bar BC. 5 can be represented as A B bar C. Min term of 6 is A B C bar, and min term of 7 is A B C. Now, if you observe the first and second and last, so what is common from second and last? We have AB common, C plus C bar remaining, and if you observe second and third, we have C, A bar B plus A B bar. Okay, and then you can write AB plus of C dot A XOR B. Can I write like this? This is a modified carry expression. Can I write like this? This is not the minimized expression. Remember, when we have a minimized expression, the delay will be minimum. This is a modified expression of the carry. Now, by observing this modified expression of the carry, and we know about the logic circuit of the half adder as well. We know about the logic circuit of the half adder as well. These two things make us able to construct a full adder by using half adders. Now we can construct a full adder by using half adder with the help of this modified. Please observe here, beta ji. So implementation of full adder by using half adder. Please observe. We have already half adder. In half adder, we have one XOR gate, one AND gate. This is a half adder. Is it okay? Yes, sir. So we have a half adder. Half adder can be represented in this way. Is it okay? Yes, sir. I want to implement A XOR B XOR C. So AB is here. So we will get A XOR B and we will get AB. If I use C and this, then we have some bit coming as A XOR B XOR C. And the sum bit will suffer 2 XOR gate delay as in the previous case. Is it okay? But if we observe carry, we have AB, and what is the function we are getting here? So A XOR B, and this is C. So we are getting C dot A XOR B. If you observe the modified carry expression, we have AB plus C A XOR B. It means we need one OR gate as well. So we need one OR gate as well. Now we have AB plus C A XOR B, which is nothing but a carry expression only. So one full adder can be implemented by using two half adder and one OR gate. How many of you can see this? One full adder can be implemented by using two half adder and one OR gate. This circuit is very important, especially for the look ahead carry adder circuit. Okay, or in a ripple adder as well, we are using this circuit. How many number of logic gates are there? Sir, 1, 2, 3, 4, 5. Oh, sir. Now I am able to understand why you have modified this expression. How many number of logic gates are here? We have 6 logic gate. How many number of logic gates are here? We have 5 logic gates. Same function will be implemented with a reduced cost. Yes, sir. Suppose if XOR gates will have a delay of 2 TPD and basic gate will have a delay of TPD, then how much time it would take to have some bit and carry bit available at the output? If XOR gate will have a delay of 2 TPD and basic gate will have a delay of TPD. So XOR gate will have a delay of 2 TPD, then this will take 2 TPD time, this will take 2 TPD time. It means some bit will be available in 4 TPD time. However, here 1 TPD time and 1 TPD time. So this will take 2 TPD time. If we go with a minimized carry expression, then carry generate faster. Is it okay? No doubt. Yes, sir. The modified expression, if we observe, if the XOR gate will have 2 TPD delay, this XOR gate will have 2 TPD delay. It means the sum bit will be available after 4 TPD. This will have 1 TPD delay. This will have 1 TPD delay. But instead of 1, because of this 2 TPD delay, so until unless the input is not available, you can't go to the output. Is it okay? So this will be available post 2 TPD delay. After that, it would take 1 TPD delay, so 3 TPD delay. And after that, it would take 1 TPD delay, so 4 TPD delay. So it means carry is available post 4 logic gate delays as well as sum is available post 4 TPD. So both carry and sum is generating at the same time and the number of logic gate is reduced by 1. Is it okay? This circuit is not faster. Instead of this, your previous circuit is faster because that is implemented by the minimized expression. Is it okay? In case if each logic gate will have same delay, then definitely this circuit is faster and this is the best case that we can use. But in order to reduce the cost, and since almost both the circuits have the same speed of operation for the sum bit, so we can proceed with a 2 half adder and 1 OR gate as well to implement a full adder circuit. How many of you able to understand, Betaji? How many of you able to understand this concept? Please let me know by writing in the comment section. I'm just removing this. How many of you able to understand up to this? Please let me know by writing in the comment section, Betaji. How many of you able to understand up to this part? Please let me know by writing in the comment section, Betaji. How many of you able to understand up to this part? Please let me know by writing in the comment section. So one full adder can be implemented by using 2 half adder and 1 OR gate. One full adder can be implemented by 2 half adder and 1 OR gate. These things are very important when we are going to learn the group adders. How many of you now able to understand, Betaji? Great. Let's move to the next part, that is half subtractor. We are not interested to design a subtractor circuit. We are always interested to design an adder circuit. Why? Because whenever we have to do the subtraction, the 2's complement numbers, 2's complement of a number is representing a negative number. So we will perform the addition of one positive number and one negative number. Automatically subtraction will be done. So we are always interested to design a adder circuits only. Actually, we always use adder circuits. Is it okay? But let us suppose if we want to design, can we design a subtractor circuit? Yes, sir. How can we design a subtractor circuit? Please observe. Sir, to design any combinational circuit, it is very easy. We need to follow the only 4 steps. First is to identify the inputs and output, construct truth table, write logical expression, minimize it, and implement the logic circuit. So we are interested to design a half subtractor. Half subtractor is a combinational circuit which performs subtraction of B from A, where A and B are 2 1-bit numbers. Is it okay? It is a combinational circuit to perform subtraction of B from A. It is a combinational circuit used to perform subtraction of B from A, B from A, where A and B are 2 1-bit numbers. A and B are two 1-bit numbers. Is it okay? Yes, sir. So we want to design a combinational circuit to perform A minus B. Is it okay? Can you design? Yes, sir, we can design. How to design any desired combinational circuit? First of all, we need to identify the inputs and outputs. So I'm interested to design a subtractor, half subtractor. So we have two input. Already I have indicated A and B. We need to perform A minus B. Is it okay? When we do the subtraction, we will get difference and we get borrow. We will get difference and we get borrow. Maybe we have to take borrow. If we are taking borrow, then borrow pin will become high. If we are not taking borrow, borrow pin will remain low. Is it okay? Because whenever we are doing the subtraction, there is a possibility that we subtract a higher number from lower number. Under such a condition, we can't do the subtraction, so we must need to take borrow. Is it okay? Great, sir. So now you know about the half subtractor. You want to perform a difference A minus B, arithmetical operation, not as an expression. And in case if we have to take borrow, borrow pin will become high. So we know about the inputs and output. Next is to construct truth table. So if you observe, the truth table is the table between inputs and outputs. We have A, B, and output is in difference and borrow. Output is difference and borrow. Is it okay? Yes, sir. So we have 0, 0. How many possibility with the two 1-bit numbers? 4 possibility. Either both are low, any one of them is high, or both are high. So it can be represented in terms of a binary of 0 to 3. 0, 1, 2, 3. Is it okay? How you will get difference? A minus B. A minus B. If we are getting if we are going to perform A minus B, then can you do 0 minus 0? Yes, sir, we can perform 0 minus 0. 0 minus 0 will give you 0, borrow 0. Can you perform 0 minus 1? No, sir, we can't perform 0 minus 1. Can you perform 0 minus 1? No, sir, we can't perform 0 minus 1. What we need to do? We need to take borrow. And if we are taking borrow, since the base is 2, so we are getting 2. 2 minus 1 will become 1. How many of you are able to understand? Let me show you the borrow concept once again. Suppose, just I am explaining you. Please observe. Please observe. Suppose if you have to perform 563 minus 197. Can you perform this subtraction? Yes, sir. How would you perform this subtraction? You can't perform 3 minus 7. So what you do? Sir, I will take borrow from here. Since this is a base 10, decimal number. So when you take borrow, this will become 13 because you are taking the borrow from 10 splits. Okay. So if you take borrow, this will become 13. 13 minus 7. So this will become 6. And what is left out here? Here we have 5. So 5 minus 9 we can't do. We need to take borrow. So when we take borrow, again, this will become, because the base is 10, so this will become 15. Is it okay? Yes, sir. So 7 and we have 15. 6 only, na? Yes, sir. 9 plus 6 is 15. And then we have left out is 4. 4 minus 1 is 3. So 366 we are getting. Is it okay? In the same way, suppose if we have a number 0, 1, 1, 0 and we want to perform 0, 0, 1, 1. So how would you do the subtraction performed here? We need to take the borrow from here because the base is 2 in binary. So here we are getting 2. 2 minus 1 we are getting 1. Is it okay? Yes, sir. In the same way, whenever we have to take a borrow, then borrow pin will become high. So can you perform 0 minus 1? No, sir, we can't perform 0 minus 1. We must have to take borrow. And if you are taking borrow, borrow pin will become high. Now this will become 2. 2 minus 1 will be 1. Is it okay? In the same way, what is 1 minus 0? What is 1 minus 0, beta ji? What is 1 minus 0, beta ji? What is 1 minus 0? So, sir, 1 minus 0 is 1 only, sir. And borrow 0. What is 1 minus 1? 0. Borrow 0. How many of you are able to understand the difference and borrow in case of a half adder now? Great. So, in a half adder, now we have difference logical expression will become difference, logical expression will become A bar B plus of A B bar. Is it okay? Yes, sir. A bar B plus of A B bar. We are getting here high and here high. That is 1 and 2. So this will give you A XOR B. A XOR B. And what about borrow, beta ji? The logical expression for borrow. Logical expression for borrow will become, sir, we have only one position where we are getting borrow high, and that will become A bar B. So we have a borrow, that is A bar B. How many of you able to understand the circuit for a half subtractor now? Yes, sir. The half subtractor can be represented in this way. A XOR B. We can represent a bubble A bar B. So this is your difference A XOR B, and borrow we have A bar B. How many of you able to understand, beta ji? Please let me know by writing in the comment section. So what is the basic difference between the sum bit and borrow, half subtractor and half adder? There is only a half subtractor and half adder. There is only one difference, that is this borrow. Is it okay? Yes, sir. How many of you able to understand up to this part, beta ji? Please let me know by writing the comment section. Okay, in the full adder, I have to write one more line that I forget. You can just put here. There is one line I missed here. This one line is in the full adder. You can just put anywhere a full adder and write down a note point. In full adder, we have number of NAND oblique NOR gate required to implement full adder is equals to 9. For full adder and full subtractor, we need 9. For half adder and half subtractor, we need 5. Okay. So it will be very easy to remember. Okay. How many number of NAND gate is required to implement half subtractor? So number of NAND oblique NOR gate required for half subtractor is equals to 5. Is it okay? Very easy to remember. How many of you able to understand up to this part, beta ji? Sir, can this complete course will be done before July? Because I am running very fast. It will be most of the portion will be finished, but it goes in the July part as well. Okay. Digital is a small, but not so small. It can't be done in just 2 or 3 days. How many of you able to understand up to this part, beta ji? Please let me know by writing in the comment section. How many of you able to understand up to this part? Please let me know by writing the comment section. Is it okay? So we have a adder and subtractor. Can we design a circuit where we can put plus to add, minus to subtract? Yes, we can do. We can design single circuit for half adder and half subtractor by using controlled XOR gate. We can do by using controlled XOR gate as well. Is it okay? So how to use a controlled XOR gate? Sir, very easy. We all know a XOR gate can act as a buffer as well as an inverter. We all know about the XOR gate. XOR gate can act as a buffer as well as an inverter. So if we are performing A, B, this will give difference or borrow A XOR B. That is difference as well as borrow, both will have the same. If we talk about AND gate, adder, so for adder we have AB. Is it okay? Yes, sir. For adder we have AB as a carry. So I can use here a control input. If this control input is 0, it will act as a buffer and we will get AB. If the control input, or you can say carry means half adder operation will perform. If the control input is 0, then we will get A bar, and A bar B is a borrow. Is it okay? Yes, sir. So all of you can see that if control input is 0, then half adder operation, and if control input is 1, then half subtractor operation, because if the control input is 1, it will act as an inverter. If the control input is 0, it will act as a buffer. How many of you can able to understand? We can do at plus and minus as well. So this is just an indication. Actual calculators are not going to use this because we never design a subtractor circuit. We have only adder circuit. A 2's complement number is representing a negative number, and whenever we have to perform a subtraction, we can just do the addition. How many of you able to understand up to this part? Please let me know by writing the comment section, beta ji. Great, great. Hoping all of you able to understand up to this part. Hoping all of you able to understand up to this part. Is there any doubt in this? Is there any doubt in this? Please let me know by writing in the comment section, beta ji. Is there any doubt in this? Please let me know by writing in the comment section, beta ji. Is there any doubt up to this part? Great. Is there any doubt up to this part, beta ji? Great. Now next, write down binary number representation. So already it is 23:15. So I'm keeping the class up to this part only, and we'll discuss the rest of the part of overflow, concept of overflow as a 2's complement tomorrow, along with the group adders, where we will learn about the serial adder, parallel adder, look ahead carry adder, multiplexer, demultiplexer, and decoder. Is it okay? So rest of the part I will discuss tomorrow. Hoping you have enjoyed the session completed so far and able to understand everything. Please let me know, beta ji. Okay, so I am giving some questions for today as well. This is your homework question for today. And please do these homework questions. Please do these homework questions. This bar is not there. Just remove this bar, okay? Okay. So I'm just giving you some questions as a homework, and please try to solve these questions. We'll discuss in the upcoming classes and also onto the Telegram. Okay, Telegram is Varun sir @Varun sir PW. So all of you are knowing this is given in the more section. In the video, if you observe, there is a more section. In the more section, you can see the details of all respective groups along with my group. Okay, great. Any kind of suggestion that you want to give for the classes, just let me know. If you want to have any kind of suggestions for the classes, whether you will be able to understand the things, you will enjoying the things, or you want to give some suggestions for any change. I just wanted to have a little bit talk with you, because I am only moving with the content, and maybe because of lot of content, all of you get little bit suffered, huh? So any suggestions? See, if I make the class little bit shorter, definitely it is possible. There is no issue. I can make only 40 minutes of classes, but you all know that we can't cover the syllabus then. No one can do. So if I got a time for 40 minutes, 30 minutes, it is possible for me to complete in 30 minutes as well. But definitely then many of the things I'm going to eat, not going to show you. So if something gets summarized, definitely most of the things are going to be missed. So I don't want to miss anything. Okay. Great. So hoping all of you are, this is one of the best. Thank you, Betaji. So lots of love. Thanks a lot. Good night.